Okay, it's my pleasure now to introduce Rahul Pandharipande, who is we sit on the editorial board of Invenciones, so we've been exchanging, but it was quite an interesting experience for me to sit on this committee and being locked with Rahul and other people of the committee for several days. Now, Rahul is a distinguished algebraic geometer who was in Princeton and Harvard before joining Zurich. And he collaborated with many people that we know quite well here, like Nishita Nekrasov, Andrei Okunkov, Nick Katz, and others. Today's lecture will be about curve counts on K3 surfaces and modular forms.
Okay, thanks for the introduction, and thanks for the IHP and the ABO for organizing this event. Does it work here? So I want to explain just more or less one idea. It's about K3 surfaces. And more or less, this talk is about explaining why K3 surfaces are attractive, and they are among the really beautiful objects in geometry. And it's this idea I want to convey along one line. So we start the beginning here. What is a K3 surface? So they can be introduced in a rather concrete way, which I will start with here. So we take the projective space. Does this point? This is, So there's projective space CP3, and we have these projective coordinates, these 4 projective coordinates. That's complex projective space. And the simplest approach to surfaces anyway is by writing an equation. And here we look at an algebraic hypersurface is defined by the vanishing of one polynomial. That's one polynomial that's in this polynomial ring. But I pick a homogeneous polynomial because these are homogeneous coordinates. This is the simplest way to write a surface. It's the vanishing locus of one polynomial. And an example for this is the quadric surface. If I take this polynomial to be a quadrat, let's say a sum of squares, and if I pick one that isn't so bad, I will get this shape here. These are the real points. Here, this is complex projective space. Of course, I don't draw the complex points. I draw the real points. And you get this very nice quadric surface. And it's ruled by lines, which means that this surface has this property, which is not completely immediate if you just see the shape, is that it's covered by straight lines. In fact, infinitely many straight lines. There's straight lines this way, and there's straight lines that way. This is apparent if you store spaghetti in your kitchen. If you store it in these cylindrical canisters, the spaghetti falls. And when it falls naturally into a quadric surface. This is exactly what this is here. And this theme of these lines on the surface is kind of crucial to the talk. And this is the first example. This is not a K3 surface. It's a quadric surface. OK, so surfaces come of different types. We're interested here in surfaces that have no singularities. And the easiest way to explain this here is I can take this 4 partial derivatives. And I want these 4 partial derivatives to have no common solution. Then if I look at the 0 set, this defines a non-singular 2-dimensional surface. There's no singularities at all. In this previous case, this is smooth everywhere, no singularities. So this is the degree 3 example. This is a really famous object in geometry, the cubic surface. It's if I take the polynomial FD to be a cubic polynomial, it's a more complicated shape, and you can't make this so easily out of spaghetti. In fact, it's impossible to make it out of spaghetti, because it has only 27 lines. And it's of course a nonlinear object, but it has lines on it. It has exactly 27 lines. These are famous 27 lines on this. It's hard to see. This particular one is a real manifestation where all the 27 lines are.
Why is 27 important?
Well, it's so it is so one thing that's important has a finally many number of lines. This is an important thing. So we started with the quadric with infinitely many. This says finally many. The number 27 lines is related to lots of geometry of classical geometry of 6 points on a plane. And it fits in a sequence of numbers. So I mean, the number 27 by itself is just the number 27. But in fact, it interacts with lots of classical geometry. And in fact, it's not the direction of this talk. So this is degree 2 was the quadric surface. Degree 3 is the cubic surface. And you see we went already from infinitely many lines to just 27 lines. So we lost almost all the lines. So, so we've discussed here these surfaces of degree 1. Well, we didn't discuss 1. 1 is just a plane. It's almost too boring to discuss. So there's degree 1, 2, and 3 what we've discussed. And these are surfaces that have rational parametrizations, which means that I can parameterize the solutions by just two variables and a rational function. And this is a special thing. In fact, the rational functions, well, it's a special thing. And for a plane, it's obvious. There's something you learn in high school. You can parameterize a plane by two functions with rationals. For the quadric, it already takes a little more intelligence to do it. For the cubic, it's a little bit non-trivial to parameterize that. But you can do it. It's a result of somewhat more sophistication that says that if I go to degrees 5 and more of these surfaces, they don't have any of these parameterizations. They're what's called general type. They're irrational. You cannot parameterize them by rational functions. And to say this very extremely is that, in fact, if I take a random one of these, then in fact there's not even any rational curves. There's no way to put any rational curves. So in particular, there will be no lines at all. Not only no lines, but no rational curves of any degree. You can't even, not only can you not parameterize the whole surface by two variables, you cannot even find a rational, any map of the complex numbers given by rational functions there. None at all. So what happens is there's this transition here. In degrees 1, 2, and 3, the whole surface is rational, and you can find, of course it's rational, you can find lots of rational curves. And in degree greater than 5, there's almost none. In fact, they can be taken to be none at all. So there's a transitional degree here, which is the degree 4. So non-singular hypersurfaces of degree 4 are chordate K3 surfaces. This is the easiest way to come to a K3 surface. It's a very simple thing. I take CP3 and I write any non-singular chordic equation. In fact, the Fermat chordic, the sum of the powers. This is a zero set. It's a zero set in complex space, and this is the first example of a K3 surface. And it has this kind of transitional feature here between this phenomenon of things with lots of rational curves, rational parameterizations, and those with none. So it's a transitional operator. This is one of the reasons, one of the points of interest of it, and what will be explored here. Okay. So now I tell you some things about this surface. I told you, in some sense, I explained one of them, which is this chordate K3, and it's a very simple equation, but underlying that equation is a lot of interesting geometry. So it turns out the cohomology groups of these, which is somehow measures the holes, they're in 0, 2, and 4, and they have this z plus 22, z, and z. The Euler characteristic is 24. And there's an intersection pairing, which is when you have this surface, when I say surface, it's two complex variables, four real variables, and there's a pairing on the H2 and H2 to Z, and this is a 22-dimensional lattice, and it's given by this U, E8, E8, and here's the lattice. So already all the structure is hidden already in just that chordic equation. So this is somehow the topology of this K3 surface. So maybe I come back here. So this is a particular example of a K3 surface. If I wanted to say what are K3 surfaces, in fact, if I take the underlying differential geometry of this K3 surface and put any complex structure on it, that's what a K3 surface is, or I could put an algebraic structure, but it's any different complex structure I put on this. Now, a fancy way to say this in algebraic geometry is that an algebraic K3 surface is any compact, simply connected, non-singular algebraic surface with trivial canonical class.
Does key stand for?
Yeah, we come to that. We'll come to Cedric's question in a second. So for a K3 surface, the underlying differential manifold is always the same. It's just that quartic. All that's changing is the different holomorphic structure. And so the point I wanted to make here is that with respect to rational curves, K3 surfaces lie between the rational surface with lots of rational curves and surface of general type with none, or a paucity. And here, this is in the study of surfaces, it's a little bit like elliptic curves. So when one studies elliptic curves over Q, I mean, this is a long, rich topic, but the elliptic curves over Q play a similar transitional role. If I take curves of lower genus, genus 0, they have lots of points over Q, and curves of higher genus have few or none. This is a Mordell type theorem. So it's the arithmetic analog of this. And these elliptic curves play this transitional roles that play a transitional role for the Q points that K3 surfaces play for the rational curves. So since I've shown you pictures of the quartic and the cubic, then I show you one of the K3. This is a Kummer K3, a particular K3 surface. And it has, this is, of course, when I show these things, these are the real points of some K3 surface. This is actually a 3D printed model that's commercially available. I have one in my office. All right. So, so to Cedric's question, the K3 surfaces, so they were named like many objects in 20th century mathematics by André Weil, and they're named after these three mathematicians, Kummer, Kähler, and Kodaira, who contributed all of them to the theory of algebraic surfaces, and in particular to the development theory of K3 surfaces. And it's always said that Weil had these three in mind, and also the peak K2 in Kashmir. That's this is what's always said, and you know whether this is anyway. So that's a picture. This was the first picture of K2 taken. It was taken by a Swiss doctor who was a mountaineer. Okay, so somehow the reason for this is that K3 surfaces are extraordinarily beautiful things. And most people who start thinking about K3 surfaces in their careers can never really ever stop. And that's okay, so we come to this question, which was not resolved. Are there any rational curves on algebraic K3 surfaces? Because I remind you, when we considered these K3 surfaces, the surfaces that were given by single polynomials, the ones that were below K3 had these rational curves, but they were dwindling in number. We started with infinitely many for the degree 2, and we went to finitely many for degree 3. And then by the time we got to degree 5, there were none. So it left open the question, what happened in degree 4? So we can consider this problem. Are there any rational curves? So this is the interesting question. And so let's try to address it. And a nice way to address it is using more or less high school algebra. And that is the question. Let's try to write. We can just try to write a rational curve. So we take a quartic K3 surface that's given by a quartic polynomial. And you can just imagine this is just the Fermat quartics. There's the sum of fourth powers. Or any one of the quartic, any other quartic polynomial you like, but just imagine you had this as an explicit one. And I want to now try to find a rational curve. So how do I do that? Well, what is a rational curve? A rational curve is a map from CP1 to CP3. And how you write a rational curve is you write down 4 polynomials of any degree. You pick some degree E, you write down 4 polynomials, and this gives you a map from these 2 variables of CP1 to the 4 variables of CP3, and this is a rational curve. So the rational curves in CP3 are parameterized by these 4 tuples of polynomials of some fixed degree. You get to decide what degree. If this degree is 1, then you'll write down an equation of a line. If this degree is 2, then you write down an equation of a conic in space. If this is 3, you'll write down the equation of a twisted cubic in space. But once you fix a degree, the rational curves are given by a 4 tuple of polynomials. And how do I know whether this rational curve sits on this quartic K3? Well, I just feed these polynomials to this equation, and I should get 0, because this curve, every point on this curve should satisfy this equation. So it's a very elementary thing. And this, as I said, this is essentially if I state it this way, it's a problem that's stated in a completely elementary way. I have this equation, I have this degree, and I can ask whether I can find these polynomials that satisfy this. And this is a linear algebra problem. And we start with some problem that's nonlinear algebra. It's somehow nonlinear, but this is a linear algebra problem to find these polynomials that satisfy this. Once I fix this degree E, this is a linear algebra problem. So we can, one thing that's good about linear algebra is that we know how to do linear algebra. And once we have a linear algebra problem, we can kind of see whether we're going to have a solution or not. Or we can try to see. So here, how do you find out whether you have a solution of a linear algebra problem? Well, the basic way is to figure out whether you have more or less equations than unknowns. This is more or less how you figure out whether you have a solution of a linear algebra problem. So we have to count. How many unknowns do we have? Well, how many spaces what's the space of possible maps here? And the answer, this is 4 times e plus 1 minus 1 minus 3. So it equals this. And what's the justification? This is the number of homogeneous polynomials of degree E. The number, I mean, this is the dimension of the vector space of homogeneous polynomials of degree E. And we have 4 homogeneous polynomials of degree E, so it's 4 of these. Minus 1 is because of the projectivization, because we're doing everything in projective space. And minus 3 is because we can reparameterize. So this minus 1, minus 3 is a little bit more than linear algebra, but anyway. So this is the number of variables we have, and how many equations do we have? Well, we have to find out how many equations does this impose on the coefficients of these polynomials. And the answer is 4e plus 1. And the reason is that this is the dimension of the space of homogeneous polynomials in degree 4e. If we want this thing to be 0, and it lives in a space of degree 4e plus 1, that's 4e plus 1 conditions. So this is the kind of elementary calculation, I'd say more or less high school algebra, that says if I want to find this rational curve on this quartic, I have this many dimensions and this many conditions. And so you see the number of conditions exceeds the number of dimensions by exactly 1, and the matter looks unfortunate for finding a curve. So this calculation suggests S4 contains no rational curves because the conditions exceed the available dimensions by 1. And yeah, so that's the situation. But it's not exactly conclusive because it is the case, for example, in linear algebra, that if you have more equations than variables, you still might have a solution. You can't rule out the possibility. But it makes it a little bit unlikely. OK, so on the other hand, let's think about the problem again. This is a really concrete problem. We have this quartic equation. Can I find a rational curve on it? And so I can take this quartic equation, and I throw it on the floor. What happens then? There. I take the quartic and I threw it on the floor. This H is the floor. It's a plane. If you take a surface and throw it on the floor, what happens? Well, it lands in some points. And in fact, it lands in 3 tangent points, because that's what happens when you throw things on the floor. So if I take this K3 surface and throw it on the floor, I get a tritangent plane. That's a plane tangent in 3 points. So S lands on a tritangent plane. What is a tritangent plane? Well, if I look at the intersection of S4, that quartic K3, with this tritangent plane, I get this. That's a quartic curve with 3 singular points. Those are the 3 tangent points. So it's a quartic plane curve with 3 singularities. This is well known to be a rational curve, actually. If you take a quartic curve, if you take a curve in the plane that's a quartic curve, it has what's called genus 3. And every time you have a singularity, it lowers the genus by 1. We've lowered it 3 times, you get a genus 0 curve. This is a construction of a rational curve on the K3 surface. And now you could wonder, is this a rigorous construction? Because it involved throwing it on the floor, for example, which is not really an established rigorous step in mathematics. So anyway, we can view this as an argument that perhaps it does contain rational curves. This argument, I think, can really be made rigorous if you try to, we're talking at the beginning about K3 surfaces defined over the complex numbers. The parts you throw on the floor can really probably be the parts defined over the reals. And, but more or less, it's a reasonable argument. It's a rather convincing argument there's rational curves. So those are the 2 sides of the dimension count says no rational curves, but we can really construct rational curves. OK, so now we come to curve counting, which is if there are rational curves, how many, etc. And this is a subject that with really kind of old roots in the 19th century. Schubert, Zeuthen, Hurwitz. And in the late 20th century, the subject took a different turn. And this was related to ideas of Gromov and symplectic geometry and Witten and string theory. And there is now, by now, a very nice framework for addressing these questions about existence and counting. And there's something special happens in K3. And here I explain that K3 is a very special kind of space. And it's what's called the Calabi space. It's a Calabi condition. It says this Chern class is trivial. This is a fancy way of saying this 4 that we found between there's 1, 2, and 4. 4 is this Calabi condition. And what has this idea that in these Calabi cases, there's a possibility of exact solutions in all genera. These are kind of exactly solvable problems. And the history of this is that in dimension 0, when x is a point, this is this theory of Witten-Kontsevich from 1992, which is related to this KDV hierarchy. And this is it leads to exactly solvable. The curve counting leads to exactly solvable problems. And in dimension 1, the K3 surface is an elliptic curve, E. And this was solved by Andrei Akunkov and myself in 2006. And that again, you get exact solutions in modular forms. And in dimension 2, what's Calabi or what's abelian surfaces, and K3, which is our topic here. So one perhaps expects this possibility of these exact solutions in this case. Of course, in dimension 3 is Calabi threefolds. There's thousands of families of these. And there are more or less exact solutions for genus 0 rational curve counts. In higher genus, this is kind of an open subject. I will make some comments about this later. But this is how this K3 fits in this world. That you, in these special geometries, you expect this curve counting problem to have exact solutions. And this is part of the departure from the world of Schubert, Zeuthen, and Hurwitz. OK, so we come back now to our K3 surface, and we look at some class. This is the class that the rational curve will have. This is a class. And you have this moduli space of maps. These are maps from these curves. This is a higher genus curve now to the surface. And it's there's a certain moduli space of stable maps. And if you view this appropriately, it has dimension G, this moduli space. So when G is 0, it has dimension 0. It's a finite number, and you can count it. So here, so this is some kind of theory about how to count it. And this theory suggests when G is 0, there's finitely many, so we can count it. So we're going to try to count now. The simplest way to count is the K3 surface might be fibered in elliptic curves. This is a very nice example of K3 surfaces. You can have a K3 surface. It maps to P1, and the fibers are elliptic curves. And then you can say, well, how many of these fibers are rational? By Euler characteristic reasons, we know the Euler characteristic of this is 24. And it means that there's actually 24 of these fibers which are rational, 24 nodal fibers. So this is a classical number. It's known for a long time that if when you have a K3 surface and you map it to a P1, it can be fibered in elliptic curves. And if you're in a generic situation, there'll be 24 nodal fibers. So in this particular geometry, we find for rational curves that they exist, and there's 24 of them. OK, then a situation which is more sophisticated, but also essentially classical algebraic geometry, is another way to find a K3 surface. So I told you how to find K3 surfaces in space by equations of one equation. Another way to construct things is taking a surface, P2, and taking a branch cover. This is another way to make new surfaces. Instead of having them as hypersurfaces, having them branch covers of surfaces you know. And the simplest surface is CP2. And I want to branch it on some curve to make a K3 surface. And if you do a calculation, it turns out you have to have a sextic. This 6 plays the role of the 4 for the degree. There's some particular degree that's right, and it turns out to be 6. It's a sextic. And it's a very old fact in algebraic geometry that a sextic has 324 bitangent lines. I draw a picture of it. So here's P2. This green is the sextic. And here's a bitangent line. The sextic has a curve in the plane, has infinitely many tangent lines, but only finitely many bitangent lines, because it's two conditions to be bitangent. And it's an old result in algebraic geometry that the sextic has 324 bitangent lines. These things go back at least to Plücker's formulas in the 19th century, probably further back than that. Every time I draw this red bitangent, I go to the double cover, which is this K3. This K3 is branched on this green curve. And these tangent points go to nodes there. And it turns out every single straight line here gives me a rational curve, a two-nodal rational curve. And for such K3 surface, there's 324 rational curves. These are the first two numbers in the counting. And this is the definition of the count. It's kind of a fancy definition because it depended on all this development in the end of the 20th century. But if I take any class on the K3 surface that has this self-intersection 2h minus 2, I define a number, which is the number of genus 0 curves in this class. And this is some intersection product in algebraic geometry. But anyway, this is the number. And it's a number when, so we start here. So then now is really the departure of the talk, which is what are these numbers? What are they related to? So far, all I was discussing here was this K3 surface and the fact that it has this property that you expect this transitional aspect with curve counting. And now we can ask, what are these numbers after this development of defining these counts? And the first discovery here is this Yau-Zaslow conjecture, which is more than 20 years ago. Well, maybe about. So we consider this series. And these are the numbers of genus 0 curves, rational curves, in this H, and this H governs the actual homologous class. This H governs the class that the curve has on the surface. I explained this curve has this class beta, and we look at the intersection form, which is given by that rank 22 lattice, and it's indexed by this number H. So this H is telling you somehow the geometry of the homology class of this curve. And this idea is to arrange this in a gyrating series, that we have these numbers, and there's this q variable, and you raise to the power here. This g, this is only about rational curves genus 0. And this number here goes in that. So, and here's what this number is a very basic one, which I haven't discussed. But this 24 is a 24 I explained. This 324 is a number of bitangents to a sextic. This is also a classical number, 3,200, also known for a long time in algebraic geometry. This is the number of tritangent planes a quartic has. So I explained that I take this quartic in space. It can have a tritangent plane. That gives me a rational curve. This is the number of tritangent planes, probably a number that maybe most people never think about. But anyway, the fact is that just like a curve in the plane has a finite number of bitangents, a surface in space should have a finite number of tritangents. And the quartic has this many, 3,200 tritangents. So this is a series. And what's striking about this is these numbers were all known for a long time, on the order of 100 years. Each one of these numbers. But what wasn't known was this Yau-Zaslow conjecture. So they conjectured that if you take these numbers and you take this infinite series, this is 1 over the discriminant, which is one of the most basic modular forms. And you can try this yourself. If you expand the discriminant, this is the Fourier expansion of the modular form of the discriminant. If you expand this, you get these numbers. And this was the first connection between curve counting and the K3 surfaces. And it is kind of astonishing because, as I said, these numbers here, even the next few, were known for 100 years. But this was not known.
So they were obtained each after another with
independent
reasoning.
Independent reasoning, exactly. Independent reasoning. So this is the first connection between this curve counting and modular forms. And so here's Yau and Zaslow. And this conjecture was proven by Beauville in 1997 and Brian Leung by different methods. And so now we move to higher genus curves. So it's not so far in this talk, I was talking all about genus 0 curves, about rational curves. And now I will move to higher genus curves. And with some trying to understand what is the meaning of this kind of statement in the higher genus. Okay. So I said this was kind of a marvelous statement that captured the imagination of a lot of people, because it had this amazing synthesis of putting together all these independent questions in classical geometry into one very, very simple answer. And moreover, this answer has meaning. It's not just a random function. It's this discriminant modular form. OK, so now we consider higher genus curves on K3 surfaces. And we have this algebraic K3 surface, and we take a class. Now, as I said before, this moduli space has dimension. If it's looking at genus G curves, it should have dimension G. So unlike the rational curves, with rational curves, we expected finitely many of them. In higher genus, we expect families of them, G-dimensional families. So here I tried to draw, this is a family of curves, not just finitely many. So in order to, if you want to get a number out of them, you have to do something, integrate something or put some constraints. So here I tried to draw curves through 2 points, for example. This gives some kind of constraint. All right, so the standard way to impose these constraints is what are called Gromov-Witten invariants. And here are some formulas for them. It doesn't really somehow matter what all these things are, but there are ways of imposing constraints, and in fact, really imposing all the universal constraints you can. So this is written as an integral over this space. And here we have some cohomology classes on the K3 surface. And then there's some other fancier classes, some cotangent line classes on this moduli space. I draw some pictures, but it's not so really relevant what these things are. So here's the picture. This moduli space of curves has some cotangent line bundles. And this one of these classes here comes from some first Chern class of cotangent lines. This moduli space of curves also maps to the K3 surface. And these gamma classes come from pulling back classes on this K3. But this class of integrands are what's it took some time to understand. These are the standard integration classes that go in Gromov-Witten theory. And these are somehow all of them. You can make various other ones, and they can be expressed in terms of these. And the intuition behind what these is best to go back to the previous slide. They correspond to these very primitive things, like having some curves through points, and then maybe also putting some tangency conditions, and putting combinations of these. This is a very geometric language. And when we change it here, we've transformed this into some kind of mathematical distilling of those old geometric ideas. But more or less, these are all the classes that come from that theory. And so a question comes here is, if I put genus 0, then there's nothing I can put, because this dimension this is dimension 0, and there's no integrand, it's just 1, and I get this 1 over the discriminant. So one can wonder what happens if I look in higher genus with some integrand. So the series that's associated is I fix this genus, I fix this integrand, and I sum over this h, which is the class of the curve, q h the h minus 1. So this is the exact analog of the genus 0 problem. In the genus 0 problem, this is 0. There's no integrand here. It's not necessary. It's genus 0. So this is the analog of that genus 0 problem. And I get some cube expansion of something. And so one can wonder, what is this something? You know? So now we have to say a little bit about modular forms, or at least their Q expansions. And here is the Eisenstein series. This is a particular series. These are the Bernoulli numbers. And this has a long history in mathematics. And you can look at the Eisenstein series 2, 4, and 6. Well, so if we leave out this 2, we take the Eisenstein series 4 and 6. This is, if I just look at the algebra generated by the Eisenstein series 4 and 6, this is the ring of holomorphic modular forms, SL2 modular forms. If I put in E2, this is called the ring of quasi-modular forms. I think this terminology goes to Donzagier, to putting this E2 and calling it a quasi-modular. Quasi-modular form because this E2 isn't exactly modular. This is a funny business, that if I have this K is if I have this 2k, this is only for even. If I look at 4, 6, 8, those are all modular forms. But the particular one, when it's 2, is not exactly a modular form. There's a different development of this discussion about that. But if I look at this algebra, E2, E4, E6, this is the ring of quasi-modular forms. And of course, these are, it is not, from these formulas, it's not at all obvious that if I look at, here, for example, E8, or higher ones, these higher Eisenstein Series, it's not at all obvious that I can write them as polynomials in E2, E4, E6, but it's true. In fact, you can write them as polynomials in E4 and E6. Right? So they all live in here, in this ring of quasi-modular forms. And this ring of quasi-modular forms is naturally graded by weight. This E2k has weight 2k, and it carries a filtration. I can look at quasi-modular forms of bounded weight. And if I look at quasi-modular forms of bounded weight, this is a finite dimensional vector space, of course, because it's, it has generators given by here. OK, so that's the, so these are the Eisenstein series, this ring of quasi-modular forms, and there's this weight filtration. OK, so this is a theorem with Devesh, Malik, myself, and Richard Thomas in 2010, that actually that series, which is all the higher genus counting, is 1 over delta times a quasi-modular form of bounded weight. But the weight is bounded by the genus and the number of insertions here. And if I put here genus 0 and none of these, then this says that actually this is, you get rid of all of that because it becomes quasi-modular forms of weight less than or equal to 0, and this more or less reduces to this Yau-Zaslow. It exactly reduces the Yau-Zaslow up to a scalar, which you can fix. But this says that, in fact, all of the counting, not just the genus 0, but all the higher genus counting, it's all governed by these modular forms. It's the discriminant goes in the bottom, and you get the quasi-modular form in the top. So how is this proven, and what are the ingredients in the proof of this? Well, the first thing is it involves actually rather complicated, various results about the moduli of curves. There's no moduli of curves in the statement, but the moduli of curves itself is a very interesting space, which has an intricate structure, a cohomology structure, of which we don't know everything about, but we know some things about. And we use the things we know about this to find relations there. So these go back to Ezra Getzler and Einel in the strongest form that I proved with Karel Faber in 2005. So we really need to know a lot of what we know about the geometry of the moduli space of curves. Then we also use this solution, this exact solution for elliptic curves that Andre and I solved in 2006. So here's Richard Thomas and Devesh Malik. It's hard to photograph Devesh Malik. This was, I caught him on the street near the Rue Mouffetard last year. So in fact, this more or less tells you the structure of all of this curve counting on these K3 surfaces. What it doesn't actually tell you the full answer here, because it says that this FG is a generating series in Q. So it involves somehow an infinite amount of data, the coefficient for every Q. And this theorem says that that infinite amount of data is actually given by a quasi-modular form of bounded weight. So this is finite dimensional. And then this carries the infinitely more Q part. So in fact, it says that if you want to know what this is, not just that it's a quasi-modular form divided by the discriminant, but to know exactly which one it is, then you have to do a finite amount of calculation. You have to calculate finitely many of these coefficients in order to figure out which quasi-modular form it is. In some cases, we can say the formula, exactly which quasi-modular form is, but as a basic structure result, this is the most general. It says that actually in all of these problems, the first finitely many, and it tells you exactly how many. Will tell you in the infinite series. And in the Yau-Zaslow case, one is lucky because this space is actually, the whole thing is one-dimensional. So in fact, the very first coefficient determines the whole thing. That's what happens in the Yau-Zaslow case. OK, so this is one basic aspect of the K3 counting. And one can ask, well, what about for threefolds, Calabi threefolds? I said that when I presented this discussion about where this curve counting fits in mathematics. It fits in this land of exact solutions for Calabi-Yau curve counting problems. And so we go now to Calabi-Yau threefolds. And through Calabi-Yau threefolds, there's lots of open questions, and the understanding is not so fine as for the lower dimension 0, 1, and 2. And in essentially, it's fair to say this, that in essentially no interesting case for a Calabi-Yau threefold are there exact solutions in every genus. That's kind of an amazing statement, but there's not a single case. For some Calabi-Yau threefolds and some low genera, there are exact solutions, but for Calabi-Yau threefold, that's interesting, for exact solution in every genus, there is no example of that yet. So here's a proposal of where to look, for example. It's from the point of view of a way to make a Calabi-Yau threefold is take this S is the old K3 surface, any K3 surface, and cross it with an elliptic curve. In some sense, this is a rather simple Calabi-Yau threefold, in the sense that it comes to a Calabi-Yau threefold that interacts with both elliptic geometry and K3 geometry. And here there's a proposal. So I will here. So the geometry of this depends on three parameters. A picture here. So this side is the surface S, the K3 surface, and this is E. And if I have a curve here, I have to specify the genus of the curve. That's one of the parameters. H is the parameter that tells me how this curve looks on the K3 surface by projecting. It's some curve that has square root 2h minus 2. And D tells me when I project this curve to E, what the degree is. So this curve counting on this Calabi-Yau threefold, S cross E, is governed by these three things, G, H, and D. It's three parameters. And this is somehow one more parameter than before. So an idea that one might think is that for the K3s, we had one fewer parameter. That parameter was that D was gone. And the answer there was given by SL, more or less, the answer was expressed in SL2 modular forms. So one might hope that here we have one more parameter, that we have something that's governed by higher modular forms, so in particular the Siegel modular forms. And this is the spirit of the answer here. So we go further. So there's a count, and the count is just, we look at this Calabi-Yau, S cross E, and we fix this genus, these numbers of the curve H and D, and you want to know how many curves there are in that. And this is a question that's more sophisticated than the question about S and the question about E separately, which have been solved. All right, so then the partition function for this theory is we sum over all genera, all H, all D, and we have this U is the genus variable. Q is our old Q, which was interpreted before as this Fourier expansion of this modular form. And then we have another Q variable, Q tilde, which corresponds to the degree of the elliptic curve. So this is this full function. And you can ask, what is this function? And as I said, the spirit of this is that these are very special geometries, and you expect exact solution to this. OK, so this is a conjecture with my student Georg Oberdiek. And it says that this function, this exact function, is actually an amazingly simple thing. It's what's called chi10. That's a Siegel modular form, and I'll tell you about it now. But when I say that there's been no case where we know the answer, I mean no case where we know the answer rigorously. This is conjecture. I don't know how to prove it. So then I finish this talk by just telling you what this chi10 is. This chi10 is this whole thing you can view as something, I told you this Yau-Zaslow conjecture was something very similar, except here was delta. This was the SL2 modular form, discriminant. And that was about the simpler geometry of just the K3. When you take K3 cross E, the answer is this chi10. So here is Georg Oberdiek. And this function, it has wound its way into various aspects of the subject. It's most closely related to Katz-Clem-Waffe in 1998. This function in a different guise had appeared in their study of this heterotic duality in black holes, and also in work of Topological and Zage in 2012. And in fact, I was on an island in Holland, and I was discussing this matter with Zage some years ago, before 2012, maybe 2010. And he was explaining to me, before I was working on this problem, he was explaining to me this chi10 should appear in this subject. He basically told that to me. It took me 5 years to understand. He was right about it. That the reason he said that I also understand now, but it took a while to understand. But he was somehow, apart from all the geometry, I was talking about the modular forms, and he said, look, there's this delta, then there's something I haven't talked about here, which was some Jacobi forms. He said with the person who fits with the exact pattern of modular forms you have is this chi10. And I didn't know how to fit it in there, but actually he was right. It's this. This is the answer.
So you mentioned, you say here black hole counts?
Yeah. Yeah, this is black hole counts in topological string theory. So this is, you know, yeah. This is a sequence of ideas that, you know, has one of its outputs, and this is the investigation in string theory, has one of its successes, not exactly this paper, but the general ideas about this. One of its successes is to explain this Hawking entropy in terms of string theory. This is kind of where it sits. This was considered, as I said, it's not this paper, but this kind of sequence of ideas of. I mean, this is considered one of the triumphs of.
It's not that you are counting various categories of black hole. It is that for a black hole you are counting something which in the end looks like entropy.
More or less, yeah. But this is not exactly that. This is what's called this topological string theory.
And you say you have, so it's weird partition function with two.
Yeah, I'm going to explain exactly this partition function. It's coming in the next slide. So this is hardly a definition of, if I tell you chi10, what are you going to say? But so this 10 is the weight. It's a Siegel modular form. This is, so here, this talk ends with just explaining what this function is. That's kind of a beautiful function. So it's this Aguza cusp form. So it's a weight 10 Siegel modular form. So what its domain is on the Siegel upper half space H2. So as I said, in some sense, this makes sense because we have this one more variable. Before we had the discriminant, which was a SL2 modular form, and it takes its values on H1 upper half plane. So this Aguza cusp form takes its values on the Siegel upper half plane. Here, I just tell you what the Siegel upper half plane is. And now I have to tell you what the function is. So right now, I've just told you what the domain of that is. And the function, to define the function, we need some variables. So here, as usual, we take this QS before was the Fourier expansion. So it's the Fourier. We're looking at this in Fourier space as Q is associated with tau, Q tilde associated with Q tilde, and I look at the exponential. It's better to write in P. So here's P, Q, and Q tilde. And remember, what I want here is something that's in Q, Q tilde, and I've already changed here the variable to P. So this function here is supposed to be in P, Q, and Q tilde. So here's P, Q, and Q tilde. So what is this function, this chi10? And I should say, the discussion here is this chi10, this function of P, Q, and Q tilde, a weight 10 Siegel modular form. And the space of these weight 10 Siegel modular forms is one-dimensional. So it's just like the discriminant case. You know, that there's only one thing here. I mean, if you have this, if you come down this road, you're going to find this. There's only going to be one once you fix this 10. So here, I haven't told you what it is yet. We keep going. So here, it's going to get a little heavy here if you haven't seen these. So first is there's this Jacobi theta function. That's a function of z and tau. The tau comes in the q, which is hidden here. The z is here. Z is related to u, which is related to p. Yeah, I mean, so I'm sorry about it, but now we come to actual functions and formulas. So that's the Jacobi theta function. This is the Weierstrass-Pay function. This occurs in your complex analysis class. And now I'm going to define these coefficients C. I define these coefficients using the Weierstrass function and this Jacobi theta. But this is, I mean, unless one knows where these stuff come from, it's basically crazy, right? So we take this. These define these coefficients. And the Aguza cusp form can be expressed in various ways, but it's this P, Q, Q tilde, and I sum over these integers k h and d I put here, and in the exponent I put these c's. This is one way to define it. There's various ways to define it. This one's by Gritsenko-Nikulin. But I said if you can define it more abstractly. You define what a Siegel modular form is, a weight 10 cusp form is one-dimensional space. So this is a proposal for really an exact solution for this curve counting in all dimensions, sorry, in all genus in degree for this very particular Calabi. Here it is, this S cross E. But various parts of this have been proven. It's kind of recent, so. So I'll come at the end. Okay, that's all I wanted to say. Yeah.
Okay. What about further questions? Let me start with one. So there was this, of course, these conjectures with Yao and Zaslav. You mentioned connection with this black hole count and so on. So behind these countings, is there some physical interpretation that can be lurking?
Yeah, in the interpretations of these counts are in string theory. The partition functions are some like free energies in string theory. Well, physical, I don't know what you mean by physical.
Okay, but the free energy usually, for instance, defined with one parameter. Here we have two, or a partition function. For instance, which. Yeah, so it's because this time it's a function on some space. The parameter is usually this genus parameter, but these other parameters are some function on some space. So some space-dependent partition function. But it may be a question that's relevant here is that how can you see this modularity? And in some of the string theory approaches, the modularity comes out a little bit better in the math approaches, because you can use you can relate this expression that says curve counting theory, you can relate it by some dualities to some different algebra. And some of the algebra has the modular forms coming out of vertex operators. So from this point of view, there were some advantages to looking at it from the string theory. That stuff is also, some of the transformations there are not known how to be made rigorous.
Okay. So yeah. You said something about progress on conjecture. What can you say more?
Oh, yeah. Where are we here? Yeah, so the progress is mostly related to these H and D. So this is in all exploration of this G usually goes somehow for a ride. So the progress involves proving this in various cases. So in particular, that if this D equals 0, this is what's called this Katzklem-Waffe formula, which has been proven completely. In higher D, I think we know how to do this for D equals 1 and some ideas for 2. And there's some kind of a grid, and then some aspects of some coefficients and some infinite sets of coefficients have been matched by various ad hoc methods. I would say that to prove this requires some idea beyond what we know about the K3 surfaces. In fact, it's not the case that we really know how to compute, if I pick some big numbers here, how to compute that in finite time, which is predicted by this. I don't really know how to do it in finite time. Yeah.
You give this exact accounting formula for K3, and I wonder what is analog of this for elliptic curves?
Yeah, so the analog, so one analog of this is counting Hurwitz covers in elliptic curves. Counting Hurwitz cover, you fix an elliptic curve, you fix some ramification, and you fix a genus, and you let the sheet number go, and you put a q variable with the sheet number. You get a function of q, and that function is known to be an SL2Z modular form. This again has some history, but it was concretely written by Dijkgraaf in the 80s, I think. That if you do anything with the elliptic curve, the entire Gromov-Witten theory elliptic curve can be written also in terms of explicit formulas of the modular form. But I think the easiest way to answer your question is you do this problem of you take this elliptic curve. I draw an elliptic curve like this, and I pick some ramification conditions. For example, I could pick completely unramified. And if I count genus 1 curves with a fixed elliptic curve and unramified covers, then there's a number for every d, and I look at this q to the d. Actually, this gives me the E2, the Eisenstein. This is a lattice problem, counting lattices, and you get something like this E2. But in general, if I do put ramification here and do this, then you get a modular form, SL2Z. That's the exact analog, in fact. Yeah, you could view, in some sense, this elliptic curve is exactly solved this way. This K3 is some mix that I've shown. But then this K3 cross E gets a Ziegel modular form. That's the.
Another question? No? Okay. Let's thank you.